Okay, we are moving on to estimating the value of a parameter using what you know about a particular sample. We're going to be using confidence intervals to make these estimates. We're starting out with estimating a population proportion. I just want to review a point estimate is the value of the statistic that estimates the value of the parameter. If we're talking about a population proportion, that's P. So our point estimate is P hat. And just review from last time, P hat is X over N, where X is how many individuals have the characteristic you're looking for, N is how many individuals are in your sample. So as just an introduction to what a confidence interval is, we're going to break it down a little bit in the next slide, but a confidence interval is a range of numbers. So if I'm making a confidence interval for a proportion, that range of numbers is going to have to be decimal values because P has to be decimal values. So as an example, I could have 0.18 to 0.35 as my confidence interval. The level of confidence is the proportion of confidence intervals that will contain the actual parameter that you're trying to estimate. So for example, if I want to make a 95% confidence interval, that 95% level of confidence implies that if I would take 100 different samples and perform confidence intervals for each one, 95 of my confidence intervals would have the actual population proportion within the interval, and 5 of them would not. So 95% of the time, I'm right about my estimate for the population parameter. So you might see a confidence interval that says something like, I'm 90% confident that the proportion of students who earned an A in Intro to Statistics is between 0.18 and 0.35. Just as an example, that's the language that you'll be seeing for interpreting a confidence interval. Just like what we were doing before, most applications of statistics really rely on symmetric distributions, specifically the normal distribution. So if we want to be able to construct a confidence interval, we need to be able to say that the data is normally distributed. To do that, for proportions, you need to have your n times p times q greater than or equal to 10, and you need to have your sample size being less than or equal to 5% of the population. The center of the distribution, that's your mean for p hat, is just the population proportion, which unfortunately we don't know. The spread of the distribution is the standard deviation. Standard deviation for p hat is the square root of p times q times over n. So the frustration here is that we're trying to estimate P, so we don't know P, which means we also don't know Q. So we have to make some concessions when we're trying to make these confidence intervals about the mean and the standard deviation. But here's visually what's happening. So let's say we want to talk about an interval in which 95% of all of the sample proportions should occur. The 95% thing means we're looking at the middle 95% of the normal distribution because we're assuming that it follows a normal distribution. You need to know this idea of alpha. Alpha is like the leftover percentage of the distribution. So here's my normal distribution, here's the middle 95%. Alpha is the 5% that doesn't fit in the middle, and it gets split into two equal pieces. Okay, so there's an upper tail of 2.5%, a lower tail of 2.5%. The critical value for us is that positive z value on the right side of the mean where that yellow dividing line occurs, somewhere between 1 and 2, closer to 2 than 1. Okay, so I can actually calculate that using StatsMate like we did before. That's like finding the z alpha. You know the probability, and you need to backtrack and find the right z value. So this is one where I know the probability right here, is 0.025. That equates to the 2.5%. So if I set my stats made up for upper tail, a probability of 0.025, I leave the mean at 0, the standard deviation at 1, since I'm looking for z, gives me a z value of 1.96. So that boundary or critical value is 1.96. Okay, this tells us that the edges of that confidence interval are 1.96 standard deviations away from the mean. The mean we just reviewed on the last slide is actually the population proportion. A standard deviation is calculated depending, it depends on the probability of success, probability of failure, and the sample size. Okay, but what we're looking at is the interval is really from one yellow line to the other yellow line, and I'm saying 95% of the time the real population parameter is going to be between those two values. I don't know what p is, so what we're going to do is we're going to estimate it using p hat from a sample that I actually collected. So forgive my picture, it got a little skewed here. So I'm using p hat to estimate p. So all I did was replace p's with p hats. From the picture and using that point estimate, you can see the endpoints of a 95% confidence interval can be calculated by taking p hat minus 1.96 times the standard deviation, or p hat plus 1.96 times the standard deviation. Okay, generally speaking, it's not always 1.96 standard deviations away. That just is the z value for 95% confidence. When I calculate my z value based on my level of confidence, I'm actually going to replace that 1.96 with a more general form. That calculation, the critical value times the standard deviation, we actually call that our margin of error. That's basically the amount of wiggle room that we need to have that level of confidence. So you can just take your point estimate plus or minus the margin of error to figure out your confidence interval. If you subtract the margin of error from the point estimate, that gives you the lower edge of the confidence interval. That's called the lower bound or the lower boundary. Adding the margin of error to the point estimate gives you the upper bound, so the higher edge. Okay, and then you know already that your p hat is in the middle, exactly in the middle, but you're saying that you're estimating that the actual population proportion is within that range. To interpret the confidence interval, to try to make it a little bit easier for you, I kind of am giving you a formulaic way to write an interpretation of a confidence interval. You basically want to say I am, or we are, some level percent confident that the population proportion of, describe your individuals and what characteristic you're looking for, is between your lower bound and your upper bound. Kind of like what I said earlier, I was 90% confident that the population proportion of students who pass Intro to Statistics with an A is between 0.18 and 0.35. Just as a quick review, I sort of touched on it in that example there, but if you need to find a critical value, you're looking for Z alpha, where you know a probability alpha, okay, and you're trying to find the corresponding Z value. In our case, that alpha is the amount of the normal distribution that's not part of the interval. So like for the 95%, alpha was the other 5%. We actually needed to cut that in half because there are two tails in the picture. So we're going to use Z alpha over 2 instead of just Z alpha. And to use StatsMate, you choose the normal distribution. You're going to keep the area type set as upper tail because that's where the critical value is, on the positive side. And you're going to enter the value of alpha over 2 as the probability. So you'll need to calculate that on the side before you find the Z value. And whatever value pops up in the A box gets rounded to 3 decimal places, and that's what you're going to use as your Z value. Now, I am going to explain in a few slides how you can go directly to the graphing calculator and get the whole interval. This is just kind of the long way of finding the confidence interval. To find z-values, this is just practice. If you want to find the z-value for a 68% confidence interval, first I would choose the normal distribution from the main menu on StatsMate. I keep the area type set as upper tail, and the probability portion should be set to alpha over 2. Now, I have a 68% confidence interval, which means 32% of the distribution is not shaded in. So that's where this 0.32 comes from. I basically took 1 minus 0.68 or 100 minus 68 and got 32% or 0.32. Divide that in half, so you would have 16% in the lower tail, 16% in the upper tail. We want to put that 0.16 as our probability in StatsMate. And you leave the mean and standard deviation as 0 and 1 because you're looking for z. The z-value will pop up in the A box, and you round that to 3 decimal places. In this case, you should get 0.994 when you round it. This would be the critical value you would use in your formula if you were constructing a 68% confidence interval. Okay, so that was just a review of some stuff we did before. This is actually the list of steps you would have to follow to calculate the confidence interval by hand. First, you will need to figure out what the value of p hat is. We are going to use a convention of rounding to 3 decimal places when we do this. You need to verify that you can use the normal distribution, so you need to check if the sample size times p hat times q hat is greater than or equal to 10. We make these p hat and q hat because we don't know the value for the population proportion. And we need to verify that the sample size is less than or equal to 5% of the population. I need to figure out alpha, so I look at what confidence interval they're asking me for. Like they'll say find a 98% confidence interval or 85% confidence interval. We take 100 minus that number to find alpha, and then look for the z-value using that alpha divided by 2, just like we did in the last slide. Then you have to estimate the standard error, also known as the standard deviation. Again, I took that formula for a population. It's normally p times q divided by n inside the square root. But I don't know what p is. I don't know what q is. I just have to assume that my sample data is close enough to give us a good estimate. Then I personally like to just calculate the margin of error before I try to plug it into the interval formula. It just makes it a little bit easier. The margin of error is your critical value times the standard deviation, and that'll help you find the upper and lower bounds. You take your point estimate p hat and you subtract the margin of error to get your lower bound. You add the margin of error to get your upper bound. And then you interpret the result using that sentence I gave you a couple slides ago. Here is a full example coming up, and I actually, because of the limitations of this recording, I don't have enough time left to get through the full example. So I'm going to make a separate video going through the example problem for you, and I will post that momentarily.